Inside the Great Pyramid of Giza, 60 feet above the pharaoh's burial chamber, 5 slabs of pink granite form a ceiling that has held the weight of 6 million tons of stone for 4,500 years. Each slab weighs up to 80 tons. That's heavier than a fully loaded freight train car, lifted higher than a 5-story building, fitted with joints so precise you can't slide a razor blade between them. And here's the part that stops engineers cold. The quarry where this granite was cut sits 500 miles away on the other side of a river, with no wheels, no iron tools, and no draft animals strong enough to pull it. By the end of this video, you'll understand exactly how a Bronze Age civilization solved a transport and engineering problem that would challenge a modern construction crew using nothing but water, rope, wood, and an extraordinary understanding of physics they never wrote down as physics. You'll also see why, even with every stage of that journey mapped out, one final step still divides the researchers who study this pyramid stone by stone. So where does an 80-ton block even come from? The answer is Aswan, a granite quarry region in southern Egypt, prized for stone hard enough to survive millennia. But granite doesn't cut like limestone. The Egyptians had no iron. Their toolkit was copper chisels, wooden wedges, and something far more brutal, Dolerite, a stone even harder than granite itself. Workers spent weeks pounding grooves into the rock face with hand-sized Dolerite balls, a steady, rhythmic hammering that would have echoed across the quarry for months at a time, wearing the granite down fraction by fraction until a clean fracture line formed. For softer stone, they drove dry wooden wedges into natural cracks, then soaked them with water. The wood expanded, and the rock split along a line the builders had chosen in advance. It was slow, it was exhausting, and it worked well enough to extract blocks that modern quarrying equipment would still respect. Archaeologists have found unfinished blocks abandoned mid-extraction at Aswan, still attached to bedrock, cracked exactly where the ancient workers intended, and then left behind, likely because a flaw appeared in the stone partway through the process. Those failures are almost as informative as the successes. They show a workforce that understood the material well enough to recognize a bad block early and simply start again, rather than risk hauling 500 miles of dead weight. But cutting the stone was only the beginning. Now it had to move. And this is where the story gets genuinely strange, because the first hint of the answer wasn't found in a quarry. It was found painted on a tomb wall dated to around 1900 BC, showing 172 men hauling a massive statue on a wooden sled, while one man stands at the front, pouring water onto the sand ahead of it. For years, Egyptologists assumed this was ceremonial. Then, in 2014, physicists at the University of Amsterdam tested it in a lab. They dragged small sleds across trays of dry sand and watched the sand pile up in front, doubling the effort needed. Then they wet the sand. The dampened grains bonded together, the surface stiffened, and the sled slid through with roughly half the resistance. A detail dismissed as ritual turned out to be an engineered solution to a real physics problem. Keep the sand rigid enough to glide across, but not so wet it turns to mud. That solves movement across flat desert. It does not solve the next problem. How do you get an 80-ton block up and out of a quarry that sits below ground level? For decades, this was one of the pyramid mystery's most stubborn gaps. Then in 2018, archaeologists working at Hatnub, an alabaster quarry east of the Nile, uncovered something no one had documented before. A steep central ramp flanked by 2 staircases, riddled with post holes on either side. The system dates to the reign of Khufu, the pharaoh who built the Great Pyramid. Researchers concluded that workers mounted a stone block on a sled, tied ropes to wooden posts set into the staircases, and hauled the sled up slopes steeper than 20%, using the posts as leverage points, almost like a rope and pulley system without the pulley. It was the first physical evidence, not just a theory, of how the Egyptians solved this exact problem. And it raised the far bigger question waiting downstream. Assume you've pulled the block out of the ground, up a steep ramp, without machinery. You still have 500 miles of Egypt between the quarry and the pyramid, and dragging an 80-ton sledge that distance overland was never a realistic option. The river solved distance the way it solved everything else in Egyptian life. Blocks were dragged on sledges to a canal cut near the quarry, Timed to the Nile's summer flood season, when water levels rose high enough to float loaded barges. Workers used a sluice gate, a wooden barrier that could raise or lower the water level on command, to float the barge under the block and lift it directly off the ground without cranes or winches. One especially massive block per barge. Then the current did the rest, carrying the load north for hundreds of miles toward Giza. For a long time, one detail didn't add up. The modern Nile runs too far from the pyramids to explain how boats delivered stone directly to the construction site. Then in 2024, researchers mapped something remarkable using satellite imaging and sediment cores. An entire branch of the Nile, since vanished beneath desert sand, that once ran close to the Giza Plateau itself, roughly half a kilometer wide. It appears to have dried up gradually after the pyramids were built. The Egyptians weren't dragging stone across miles of open desert at the final stage. They were floating it almost to the doorstep. There's a smaller mystery hiding inside this one, and it's easy to miss. Every one of these granite beams didn't just need to arrive, it needed to sit level, in a chamber built from limestone blocks that were themselves stacked with a precision that still unsettles engineers today. The base of the Great Pyramid is a near-perfect square, with sides that differ from one another by only about 15 centimeters across a length of over 200 meters. Its alignment to true north is accurate to within a tiny fraction of a degree, a level of precision some modern buildings don't achieve with laser levels and satellite positioning. Researchers have proposed that the Egyptians used simple tools, plumb lines, water-filled trenches to check for level ground, and careful star sightings to fix true north, repeated and cross-checked across years of construction. None of those tools individually explains the final accuracy. It's the combination and the sheer patience of checking and rechecking over decades that most researchers now credit. Still, exactly how they held that standard across a structure this large, using nothing but rope and water, remains a detail that's still debated rather than fully resolved. Which brings us to the part of this mystery that even now, researchers can't fully settle. Getting an 80-ton block to the base of the pyramid is one kind of problem. Getting it to a chamber 60 feet in the air is another kind entirely. The leading theory involves ramps, built from mud brick and packed rubble, that spiraled around the pyramid's exterior or extended straight out from one face, allowing crews to drag the sledge upward the same way they hauled it out of the quarry. But a straight ramp, long enough to reach the pyramid's upper levels at a manageable slope, would have required more material than the pyramid itself, and there's no trace of debris on that scale ever having existed. A spiral ramp solves the material problem but creates a navigation nightmare. Turning a sledge carrying an 80-ton, 9-meter-long granite beam around a tight 90-degree corner is close to impossible without destabilizing the whole load. Some researchers, including French architect Jean-Pierre Houdin, have proposed something more elaborate, an internal spiral ramp built into the pyramid's body itself and later hidden inside the finished structure, possibly connected to the pyramid's mysterious Grand Gallery, a chamber whose true function has never been fully explained. Others argue the granite beams were handled separately from the general limestone supply chain entirely, moved up short, shallow ramps built and demolished level by level as construction progressed, so that the heaviest, most delicate cargo never had to travel far at any single stage. Mainstream Egyptology treats several of these ideas as plausible without settling on one as proven. Ground-penetrating radar and cosmic ray muon scans inside the pyramid continue, part of ongoing international research projects, and each new scan reopens the debate rather than closing it. Occasionally, these scans turn up something nobody predicted at all, like an undocumented void above the Grand Gallery, large enough to matter, with a purpose nobody has confirmed. And that's really the state of this mystery today. We know how the stone was cut, we know how it crossed the desert, we know with startling precision how it crossed 500 miles of river. What we still don't know, not with certainty, is the exact sequence of engineering that lifted 80 tons of granite 60 feet into the air and set it down with a precision modern surveyors still find remarkable, using only wood, rope, and coordinated human labor. Every few years, a new excavation or a new radar scan adds another piece. None of them, so far, has given us the whole picture, which raises an uncomfortable question for the next mystery on this channel. If a civilization without iron, wheels, or draft animals could engineer solutions this precise for a problem this enormous, what happens when we look at a structure where the stones aren't 80 tons, but 800, cut with a precision that still defeats modern tools? That's where we're headed next.